So I wanted to continue on in chapter 16, talking about the dynamics of rigid bodies. And another name we might talk about is plane kinematics. Most of our work is going to be in 2 dimensions here. Those of you that go on into mechanical will take an advanced dynamics class and get into to 3 dimensions, but we've got to start somewhere. So we'll start 2 dimensions. And some of the terms and concepts that we'll talk about would be simple translation or rectilinear translation. We're just moving in a straight line. Then we could spice that up a little bit and have curvilinear translation, where you're moving through some curve, but those 2 paths would be equal length for going from A to A prime and B to B prime would be equal length and parallel. And then we can start factoring in rotation, and the easiest type of rotation to look at is fixed axis rotation. So let's say that we were to take point A as some fixed point, okay, and think about rotation about that. So this point B now goes from B over here to B prime over there. A remains there. I mean, you could say that this is A and A prime if you wanted to. So that's fixed axis rotation, going through some angle theta. And then we could put the whole thing together. We could talk about translation plus rotation. So adding translation and rotation, and we get general plane motion. So these paths would not necessarily be the same length at that point. Now, one thing that we're probably going to do in the future is we're going to try and turn this back into fixed axis rotation, because we'll find fixed axis rotation is pretty easy to deal with. And what we'll do is we'll think about, well, let's see, if I were to extend this point up here, and I were to extend this up here, there's some point, not necessarily on the body, that thing is simply rotating about, right? Okay, so there's no requirement that it be rotating about some point on the body. We will take this point up here, and we can turn that general plane motion into simple rotation about that point there. And this becomes then our instantaneous center of zero velocity. It's going to be a powerful tool for us in the future. So that's coming up. Questions with that? Okay, so let's develop some of this. Let's say that I've got this, and I'm going to use try and define things a little better here. Let's say that I have this body, and I'll put it on an XY coordinate system. So we've got this blob, maybe it's a football or something, and we take it and we paint a couple lines on it. Okay, so we paint a couple lines on that. Take a Sharpie and put the lines on it. Paint a couple lines on it. So those lines are affixed to the body. And remember, we're going to take this as a rigid body. So the angle between those lines, we can say the angle between those lines is beta, which is a constant, right? Because if we've taken those lines and we put those lines on a rigid body, the angle between those lines would have to be a constant. So now we can, if we were to extend those lines down to our origin here, or from the origin up to those lines, we can think about 2 angles. We can think about the angle of this to this upper line, this line here, that being theta 1, and the angle to this lower line, that being theta 2. And with simple arithmetic, we could say that theta 1, that's the larger angle, that's going to be equal to theta 2 plus that constant beta, right? Okay, simple geometry here, that if you take this angle here, theta 2, and then you add to it that angle there, beta, you would get theta 1. Now we know that beta is a constant because that's fixed to a rigid body. So when I differentiate this and say theta dot 1 is equal to theta dot 2, the beta goes away, goes to 0, doesn't it? Okay, so what I've done here is I've differentiated. Here again I've differentiated. Okay, and I could say that theta double dot 1 is equal to theta double dot 2. And this has important implications. I'll come back to this in a little bit, but this is important, and certainly this is important. Well, let's get a little better handle on what theta dot is and theta double dot. We've talked about those, but let's make sure we're up to speed on those. If we want to talk about angular velocity, we'll define that as omega, the Greek symbol omega, and that would be theta dot, or the d theta dt, differentiate theta with respect to time. And then angular acceleration we'll give that the symbol alpha, which would be the d omega dt, or omega dot, or we could think of that as theta double dot, which is the second derivative of theta with respect to t. So going back to this one, theta dot, that's really omega, or the angular velocity. Okay, so that's omega. And theta double dot, that's alpha, isn't it? And this is important because what this is really saying is that any point on this body, omega is the same. If it's a rigid body and it's not deforming, any point on that body has to have the same omega. So if I look and I want to talk about the omega there, or if I look and I want to talk about the omega there, or if I look and want to talk about the omega there, those all have the same angular velocity. They all have the same omega. That's going to be important when we go forward. Likewise here, we've shown that alpha at this point, or that point is all the same. So the angular velocity and the angular acceleration at any point on that body is the same. So that's important. Probably the most important thing on this page here. Well, if we go back and we look at alpha being d omega dt and omega being d theta dt, so I come down here and take omega is equal to d theta dt and alpha is equal to d omega dt. And I solve both of them for dt. So dt would be equal to d theta over d omega, solving this one for dt. And when I solve that one for dt, I get d omega over alpha. Of course, dt is equal to each other, so I can set this equal to each other and solve for that. That looks like our old friend from linear work, right? That v dv is equal to a ds. And we can really just switching the symbols come up with that. Now, between this equation right here, and finally that equation right there, we came up with the kinematics equations when we were working in the linear system, right? Those kinematics equations. And we're going to do that again for this case. So with that, I guess I got, I need another page here. So we'll say that we have 2.1. So I'm going to start out with omega is equal to d theta dt, alpha is equal to d omega dt, and omega d omega is equal to alpha d theta. So let me rewrite those. Omega is equal to d theta dt, that alpha is equal to d omega dt, and finally that omega d omega is equal to alpha d theta, right? I mean, that was like our linear work. What would we have with our linear work? That the velocity was equal to ds dt, that the acceleration was equal to dv dt, and we had that v dv was equal to a ds, right? So we do the same thing, but except with our angular terms, rotational terms, and we come up with those. And the biggest thing to make sure that if alpha is a constant, okay, that's huge. If alpha is not a constant, what do we have to do? Well, we just come back to these equations up here, don't we? But if alpha happens to be a constant, a lot of times alpha is a constant. Sometimes alpha is equal to 0. If you have a shaft that's rotating with constant speed, alpha would be equal to 0. Or if you have a shaft that is increasing its rotational rate at a constant rate, that would be alpha is equal to a constant, right? Okay. So we do have a lot of problems with that. Not all of them. If alpha is not constant, you've got to go back here. But alpha is constant, you can start to come up with the equations. I'm not going to go through the derivation of them because the derivation is exactly the same as our linear cases. You just change your variables and go back to your linear cases. So we could say that theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. That would be analogous to our s is equal to s naught plus v naught t plus 1/2 at squared, right? Okay. And again, probably the most important thing to remember on this equation is this. Alpha has to be constant to use that. Well, some other equations that come up would be that omega is equal to omega naught plus alpha t. Again, alpha has to be constant. That would be like v is equal to v naught plus at for the linear case. And then what was another one that we used quite a bit? It would be analogous to omega squared is equal to omega naught squared plus 2 alpha. We have to be careful on this one. I want to do the alpha of the centroid. We want to make sure we're rotating and talking about the same point. And then I could just say that this was theta minus theta naught. We could say really that we have omega squared is equal to omega naught squared plus 2 alpha delta theta. And that would be like what? V squared is equal to V naught squared plus 2AS, or 2A delta S, right? Okay. So I don't know that you have to rememorize a whole bunch of equations. You could just change the variables for your linear case. And besides, more important than remember the equations is the constraint to use those equations. No matter how easy it would be with these equations, if alpha isn't constant, you're going to be wrong in solving them with those equations. Questions with that? Yes? Well, yeah. So the question is when a circle spins, the outside goes faster than the inside. And when you said that, I was wondering, what do you think about when the outside goes faster than the inside? You're probably thinking about linear velocity, right? I don't want to put words in your mouth, but were you saying that at some point here, that this velocity here, I'll draw this to scale, is larger than that velocity there? I haven't put words in your mouth with that, right? Okay, not yet. Okay, good. But this, I think we can both be correct in this, and I'm glad you bring this up, because if this is omega, we know that the velocity, we'll see very quickly, is equal to r times omega. So if I take my constant omega that I was preaching about, that's very important, r changes, so indeed the velocity changes. Yeah, you know this, if you want a good ride on the merry-go-round, you sit on the outside, right? Yeah, exactly. So then that's one of the nice questions we get to answer. We're actually both right. Other questions? Okay, good. Well, let's try a problem with constant acceleration. A nice little Derisian rotor problem. I don't know if you've seen, they look kind of like egg beaters. It has a vertical shaft, and they're going to then rotate around this axis here. It's kind of nice because then you can put the motor house down on the ground where it's easy to maintain and service and get power out of and whatnot. And the rotors rotate like that. It's called a Derisian rotor. But anyway, we've got a point A out on this thing from the center line. The center line goes up this main pole. A is 20 feet out from the center line, and B is 10 feet out from the center line. And apparently this thing was at rest. It was shut down. Killed one too many birds, or they had to fix it or something. I don't know. It was originally at rest, and it's fired up at such that the alpha, the acceleration about the center line here that it's allowed to accelerate with, is 0.5 radians per second squared. We would like to then find the acceleration and velocity of points A and B when t is equal to 4 seconds. Well, this is a constant, right? So that being a constant, we get to go back and we use those equations. So let's see if we can put this thing together. I'm going to work at point B first. So for B, let's see what we come up with. We could say in general that the acceleration in the tangential direction is equal to alpha times r. We've seen that before. So the acceleration in the tangential direction for point B would be equal to 10 feet, that's r, times alpha, which is 0.5 radians per second squared. So this turns out to be, 5 feet per second squared. Okay. So that's the tangential acceleration at b. If I want to talk about omega, I could say that omega at 4 seconds, at t equals 4 seconds, is going to be equal to omega naught plus alpha times t, right? So this would be equal to, it's originally at rest, so omega naught is 0, plus what was our alpha? 0.5 times t, which is 4, so I come up with 2 radians per second. So I know when we're talking about at t equals 4 seconds, we know that the angular acceleration, alpha, is equal to 0.5 radians per second squared. We were given that. And we just found that omega is equal to 2 radians per second. Well, that's good because I really need to find the velocity. Well, what's the velocity? We can say that the velocity is equal to omega times r. We saw that in, just saw that in this problem here, right? Velocity is equal to omega times r. So what do we have? We have 2 radians per second times 10 feet, which gives me 20 feet per second. Okay? So that's the velocity actually at b, isn't it? That's the velocity at b. Now let's see. I've got the acceleration in the tangential direction at b. To get the total acceleration at b, if I could get the normal acceleration in b and then resolve that, I should be okay, right? So the acceleration in the normal direction at b is going to be equal to what? V squared over rho is one way of doing that. We'll talk about others in the future. But we've got the velocity, that would be 20, we just found that, squared, divided by what's our radius of curvature? 10. It's out 10 feet. And that turns out to be what? 400 over 10, 40 feet per second squared. So now if I combine those, I could say that the acceleration at b is going to be equal to the square root of 5 squared plus 40 squared. So I'm just going up and using this one and this one, which gives me 40.3 feet per second squared. So there's the acceleration at b, and there's the velocity at b. Of course, we didn't have to do the vector resolution for the velocity because the velocity is only in one direction. It's only in the tangential direction, right? Okay. Now, that's for b. What's a going to be? Should be just twice those values, shouldn't it? Well, it's always kind of dangerous making that big jump, but in no place did we square the radius. We squared velocities and whatnot, but no place did we square the radius. So it's still a linear relationship. So the radius for a is twice the radius of b, and we could say the answers for a would be twice that. So you can go through that and check that. And that might be a good exercise. Start with a clean piece of paper and see if you can get the values for a and confirm that they are indeed twice that. Questions of that?
What you were just talking about. So in order to get the velocity, you have to find out rate times r and you square that with the acceleration.
Yeah, but then I divided by r again.
Oh,
Yeah. Yeah. So this is definitely dangerous here in the sake of saving time and saving paper here. I did that. And also to give you something, go home, work it out. Check it. Tomorrow, if it doesn't work out, let's talk about it tomorrow. It'd be a good time to talk about that. But I think it will work out. But like I said, that's always kind of dangerous because if something is squared on you, you can get bit on that. So anyway, let's look a little more at this. We've talked about the acceleration being v squared over rho and things like that. Are there other expressions for that? The answer is yeah. I want to start talking about fixed axis rotation. So let's clear up what's meant by that. I've got something that's rotating about this point here. That's the point that it's rotating about, pivoting about that point. And if I look at some point on the body out here, I've got this r vector from the pivot point out to that point. This point would have some velocity in the tangential direction. It would also have some acceleration in the tangential direction. And then it would also have some normal acceleration. And for argument's sake, I could just say that it's got some alpha and some omega. If it's going at constant velocity, alpha is equal to 0. But we'll just say it's alpha and omega. So if I want to talk about the velocity here, and this is a comma, if I want to talk about this velocity, remember this is in the tangential direction, it's r times omega. We've already used that a couple times today, so nothing new there. Then if I talk about the acceleration in the normal direction, v squared over rho. Again, we've talked about that already. You've used that a lot. If we swap out this r, this distance from there to there for rho, we've got v squared over r. And we could actually go back here and recognize, well, if the velocity is equal to r times omega, I can substitute that in for v squared, and I get r squared times omega squared over r, which gives us, and maybe we should have done this before the last problem, r times omega squared. So indeed, we do have a first order problem there with r. And these are just different ways of doing this. Sometimes it's convenient to use v squared over rho or v squared over r. Sometimes we want to use r times omega squared. Get you the same answer. And sometimes we know that r times omega, that's the velocity, right? So if I factor that out, I just have velocity times omega. So these are kind of new, but really just another factoring or reordering. So I'll put new in quotes. Just a little different way of looking at that. If we look at the tangential acceleration, r times alpha, we've already used that. That should be pretty straightforward. Now what I'd like to do is I'd like to talk about this with vectors, because pretty soon our problems will probably get too complicated. We can't necessarily use a scalar solution like we did in this one. This is pretty easy to use a scalar solution in. If we started looking at some different axes, or certainly as you go into a three-dimensional problem, it can get quite difficult. So with that, I could say that the velocity is equal to omega crossed with r. And remember with the cross product, so this is cross, order is important with the cross product. Okay? It's not a commutative. If I say r cross omega, I'm going to be off by -1, aren't I? So a lot of times we may want to get in the habit of writing this even in scalar form as saying it's omega times r, so we kind of get that well, hey, omega has to go first. Okay? But whether you do that or not, you want to recognize when you do the cross product, it's omega cross r. Well, you're going to use the right-hand rule to figure this out, because if you take this and omega is going this way, where in the world is the omega vector? Well, what you do is you take your right hand and you put the fingers of your right hand in the direction of omega or alpha, and where does your thumb point? Out of the page, right? Okay? So you take the fingers of your right hand, put them in the direction of the omega or the alpha, and then your thumb is pointing in the direction of that vector. So I've kind of drawn this in a 3D down here using the right-hand rule. When we were rotating around here with the omega, take your fingers of your right hand, and you know then that's your omega vector. I should put the vector hat over that. Okay. So then if we say that the velocity is omega crossed r, again, take your right hand, put your fingers in the direction of omega, rotate them to the direction of r, and which way is your thumb pointing? Your thumb is pointing kind of in that direction there, isn't it? Does that make sense for the velocity? Well, we'd know it was in the tangential direction, wouldn't we? Okay, so this is working out. The other thing, and we talked about this a lot in statics, if you're going to start to use the cross product, you have to use a right-hand coordinate system. What's the definition of a right-hand coordinate system? That if you take your fingers on the right hand, go from X to Y, your thumb has to point in Z. So this is a right-hand system. Okay? If you decide to put Z back into the page, that's not a right-hand system. So be careful. Make sure you're using a right-hand system if you're using the cross product. Well, if we go on, then we can talk about the acceleration in the normal direction. That would be omega crossed with r. Well, where'd that come from? Well, it really came from this. Omega crossed with the velocity. Okay. Now, you may like the cross product. I mean, it's a lot of work. I don't think I'd want to do two crossings. And this one, it begins to, well, if I don't have the velocity, I got to go back to this thing, right? And we get the velocity by default. Here is a very convenient one. Let's say this is nice. No quotes, exclamation point. That's handy. Okay, and it bugs students a little bit because it has a scalar term out in front, minus omega squared. Well, where'd the omega squared come from? Well, look at this thing. Okay, that's the magnitude of it, r times omega squared. I mean, if you want, I can rewrite this omega squared times r. You happier? Okay. So omega squared times r. And where'd the stupid negative sign come from? Well, our normal acceleration is in what direction? Opposite the r direction. So this r gives this direction, and the negative sign puts me going back down r. Okay. So you take this omega squared, which is a scalar. It's just going to be a number squared. Multiply it by minus 1, a negative sign, and then multiply the r vector by that. And that's actually a nice handy way of getting your normal acceleration. A lot easier than going through all of those crosses. Okay. Well, speaking of crossing, there's no quick way about this. The tangential is just alpha crossed r. And maybe having seen that, maybe I should start writing this as alpha times r. So we start to get in that habit of thinking, oh, it's always alpha first. Because again, with the cross product, alpha has to go first. Alpha crossed r. Questions with that? So trying to relate some of the stuff, v squared over rho and whatnot that we've seen and used in the past to some of this new work. What I'd like to do is maybe try this in a problem then. So let's say that we have a problem like this. Where I have some sort of a, this would be about like some sort of a framing square or something that's rotating about a point. I don't know why you'd do that, but anyway, you got a point there and it's rotating. So you got 0.4 meters here, you got 0.3 meters there, and you got this point A out here. We've shown the x and y coordinates. I've shown omega. We've got alpha that's equal to 4 radians per second squared, and it's decreasing. What does that mean? Deceleration. What does that mean in reference to the velocity or the angular velocity? It would be opposite omega, wouldn't it? If our acceleration is opposite our velocity, it's slowing us down, it's opposing, so that would be opposite omega if it's decreasing it. So what we'd like to do is we'd like to find the velocity of point A out there at the end. We'd like to find the acceleration of point A out there in the end. And those are vector quantities, and we'd like to find that when omega is equal to 2 radians per second. So probably the first thing that I want to do is I'm going to look at this point out here. I'll kind of blow up this picture with what we have there. And we're told that omega is going like this, and alpha, and that's to the tune of what? 2 radians per second. And alpha is opposing it. It's going to go opposite it, like that. So if I use the right-hand system here with the right-hand rule, I can say that omega in vector form is what? I mean, if this is my x and my y, what is z? Z's out of the page, isn't it? And if this is x and this is y, you take your hand, go from x to y, your thumb is pointing out of the page. So now we know that z is pointing out of the page. It's this axis here that's out of the page. So if you take your fingers of your right hand and put them in the direction of omega, which way is your thumb going? Into the page. Okay? So that would mean omega is minus 2k, wouldn't it? if positive z is out, omega is pointing into the page, so omega is minus 2k. What about alpha? Put your fingers in the direction of alpha. Which way is your thumb going? Out of the page. So what's alpha going to be in vector form? Let's see, we got, they told us it was 4 radians per second squared, so it's going to be what? Positive 4k, isn't it? So that's important. I'll do that again. Positive z is out of the page, so you put your fingers of your right hand in the direction of omega, and your thumb is pointing into the page. Into the page would be minus z, minus k. Alpha, you take your fingers and put them in the direction of alpha. Your thumb is pointing out of the page, so that is positive z or positive k. So we got those. Any questions with that? The other little piece of information we need to probably get is this r vector. So can we describe r? What's that going to be? 0.4 in the I direction plus 0.3 in the J direction, right? Just describe to someone how do you get from there to there. That should work, right? So let's see if we can get the velocity. What's the velocity of A? We're going to have omega crossed with r, aren't we? So that would be minus 2k crossed with 0.4 in the I plus 0.3 in the J. Is that right? So, I mean, you could set this up as a matrix. You could put it in your calculator. It's pretty easy to do by hand. What are we going to have? You're going to have minus 2 times 0.4. And what do we have with k cross I? Positive j, right? And then I'm going to add to that minus 2 times a 0.3. And then what do I have for k crossed with j? Minus I. Okay. So when we get through that, I have that the velocity A is equal to positive 0.6 in the I direction minus 0.8 in the J direction. That would be meters per second. Is that right? Yeah. This stays negative. This turns positive because I have two negatives in there. Okay. So you could go through that a variety of ways. It's pretty easy to just do by hand. Well, what about our acceleration in the normal direction? Acceleration in the normal direction for A. What could we do with that? I mean, you could say that it was omega crossed with r. That's probably the toughest way to do it. I mean, that would be what? Minus 2 in the k crossed with minus 2 in the k crossed with 0.4 in the I plus 0.3 in the j. That's kind of ugly, but I'm not going to do it that way. What would be a quicker way to do that? Minus omega squared times r, right? So I'm going to end up with what? Minus. And then I'm going to have, what's omega? The magnitude of omega is 2, so I'm going to have 2 squared. And I have to multiply this whole thing by r, 0.4 in the I direction plus 0.3 in the j direction. So when you get done with this, your acceleration in the normal direction for A is going to be equal to, I'm going to have minus 4 times 0.4, which gives me what? Minus 1.6 in the I direction. And then I'm going to have minus 4, and that negative sign is outside that, so don't let that go away on you. Don't put that inside there and have it go away. So I'm going to get minus 4 times 0.3, which is minus 1.2 in the j direction. Okay. And that would be, of course, meters per second. I'm probably going to resolve that with the tangential, so I'll just leave that. Yeah, second squared, thank you. This would be a final answer up here. This I'll probably add for the acceleration. So far, so good? I think this was definitely easier than trying to do it this way, right? I even ran out of paper there trying to do it that way. You should get the same answer both ways. You can check it out. So what if we look at the acceleration then in the tangential direction for A? What do we have? Tangential acceleration is alpha crossed with r, isn't it? So what's alpha? 4 in the k, and I'm going to cross that with r, which is 0.4 in the I direction plus 0.3 in the j. So what's that turn out to be? 1.6. 4 times 0.4, 1.6, and what's k crossed with I? J? And then I'm going to have 4 times 0.3, 1.2. And k crossed with j is minus I. Okay. So that would be the acceleration of in the tangential direction for A, and meters per second squared. So let me finish this up. So we can say that the acceleration of A is going to be the acceleration in the normal direction for A plus the acceleration in the tangential direction for A, right? Which is going to be, there's the normal, minus 1.6 in the I direction, minus 1.2 in the j direction. And then I have to add that to 1.6 in the j minus 1.2 in the I. What do we come up with? Minus 2.8, is that right? Yeah, minus 2.8 in the I direction. And what do we have for j? Minus 1.2 and 1.6 gives me plus 0.4 in the j. Okay. You could actually go through this with a scalar solution. Wouldn't be a bad way to test it, but very soon our problems will get complicated enough. A scalar solution is going to be pretty difficult. If you look at the directions of these, for instance, the normal acceleration, that's in the negative x and the negative y. Does that make sense in the problem? Yeah, I mean your normal acceleration is going to go back to the point that it's rotating about, isn't it? How about our tangential acceleration? Where is it going? Positive in the j, negative in the I? So positive in the j, negative in the I? Yeah, with the directions that are going, that makes sense. And really, we just resolved this vectorially. Questions with that? Well, where we'll go next time when we get together is we're going to start to talk about gears and powertrains. It'll be kind of interesting. Let's say that we have a small pinion gear driving a large bull gear. We'll talk about if this has some input omega. We'll be interested in even the direction of this, but what output omega that we get. So we've got some things to talk about with that. Take care till then.